In this video, we're going to be talking about the so-called surface integrals of type 1, which is a generalization of the surface area. So these integrals uh, generalize the surface area in the following way. So the idea is the following. Suppose we have a surface. Suppose we have a surface parametrized, say, just for instance, by U between A and B and V between C and D. Now, in general, the bounds for U and V do not have to be making a rectangle, but this will be easier for now. Given by the formula, okay, some parametrization T from this rectangle to R3. Then let F be a function from, say, R2 to R, or maybe R3 to R3 to R, okay, be given by a scalar valued function. So now the idea is compute the double integral over this region. Let's call it S of F ds. Now we haven't used this notation before. Let me explain what it is. So suppose I have a surface in three-dimensional space, and at every point on that space, say x, y, z, I have a function x, y, z, which is scalar valued, which is an r. And what this f does is it gives the density of this object at that point. Here, f can be interpreted as the density of the surface at each point. And this interpretation has to allow for negative density as well. This is just an interpretation. So it's possible that all the density cancels out and you get 0 at the end. The double integral given by this object right here, right, adds up all of the contributions of the mass and eventually gives you the mass of the entire object. Gives the mass of the object. Now, let's just figure out what is this ds? What is ds? This is an area element. And the way that we compute this is the following, right? So recall that we have the parametrization T is given by this right here is the parametrization. And then recall that we compute TU, right, of UV. This is the tangent vector in the U direction, and TV at UV. And then the norm of the cross product. So basically what you do is you take this integral right here, and what I'm going to do is I'm going to change my coordinates to U and V, A, B, C, D, and the inside integral is du, the outside integral is dv. Here's f, and what you do is you plug the parameterization into f, and then on the outside you multiply by this object right here, which we saw in the previous lecture. So this object right here is ds, this is f, and this is given by this. So each of the three parts is labeled in this way, and you have the density here, you have the area element here, and you have the integrals right there. Now, notice that when f is equal to 1, okay, then we have basically uniform density, and the density is 1 everywhere. So what happens is that this guy right here, this f ds, just becomes ds. If you think about it for a moment, if I have uniform density, then really what I'm just measuring is the surface area. So, and recall that our formula for the surface area okay, is given by, say, AB, CD, TU cross TV, dV, du. And then therefore this makes perfect sense because this is just plain old ds. So whenever you see this object right here, with the f being 1, we're just talking about surface area. But in the presence of an f, you can interpret it as density. Now let's do a host of examples. So let S be the surface given by z equals x squared plus y, with x and y both in, actually, let's take x between 0 and 1, and let's take y between -1 and 1. And then I want to compute the double integral over the surface S of x ds. So what does this, let me just draw something very, very general. If I have a surface and I can think of every point on the surface as having a certain kind of density. So here we can interpret the integrand, okay, as a density rho of, say, xy, in this case, is equal to x. So whatever its x value is the density at that point. The surface integral, the double integral of x ds, right, sort of adds up all of the density, and then as a result gives you the the mass of the entire object. Okay, so some problems may even ask you to find the mass and the given a density without actually writing down the integral. So you're going to have to come up with the integral yourself. So just as a note, this the integrand, right? If you interpret it this way, you have to allow for the fact that the density might be negative, even though that's not physically necessarily the case. Just interpretively, okay, this rho of xy, could be negative sometimes, just theoretically. Just like area could be negative, so can density. So in this case, what you're going to be computing is the net mass, right? The net mass. Now let's figure out how to do this, right? So here we have a rectangular base or a rectangular set of parameters. So let's just let x equal u, y equal v, and then z equals u squared plus v. So my TUV is equal to UV U squared plus V. And now I want to compute TU cross TV. Well, let's compute TU first. I get a 1, 0, 2U, and my TV is 0, 1, 1. Now let's compute the cross product. I have IJK 1, 0, 2U, 0, 1, 1. So the I coordinate looks at this square right here. This gives you a minus 2U. The J coordinate looks like this piece right here. So that's a 1, but then there's an inherent minus sign in the J coordinate, so it's a minus 1. And the K coordinate looks like this, so that's equal to 1. Now TU cross TV in norm is equal to the square root of 4U squared plus 1 plus 1, which is the square root of 4U squared plus 2. So now we're going to take the double integral of f ds over s. Now, this is given by x ds, stated in the original problem. And let's see how we would figure this out. So f of the parametrization, t of uv, cross times tu cross tv in norm, and then du dv. The u is the x, which goes from 0 to 1, and the v is the y, which goes from -1 to 1. All right, so ft of uv, right, it only just has, f is just taking the first coordinate. So f is just u, and then I have 4u squared plus 2 du dv. Now there are no v's in this problem, in this integrand. So I just take the top value of v and subtract the bottom value of v and get 2. Okay. And here, I guess we can't call it a u substitution. I would call it a t substitution. T equals 4u squared plus 2. But if you can resist doing this by u substitution and writing out all the steps, just realize this is 4u squared plus 2. Well, we have in the integrand a 1/2 power, so this becomes a 3/2. To compensate, I need a 2/3. And then here, my dt is going to have an 8u. I already have a u, so I need an 1/8. So I can just write that down. 2 times 1/8 times 2/3 is 1/6. U 4u squared plus 2 to the 3/2 from 0 to 1. So this becomes a 1/6 times 6 to the 3/2. When I stick in the 0, I get a 2 to the 3 over 2. And if you wish, you can write this as 1/6 of 6 root 6 minus 2 root 2. And that's it for that problem. Let's take a look at a spherical example. Compute the double integral of z squared ds over s, where s is the unit sphere. Now remember the parametrization of the unit sphere in terms of theta and phi. Okay, so recall that t is a function from 0 to 2 pi, that's my theta, to cross 0 phi to R3, and then t of theta phi is equal to cosine theta sine phi, sine theta, sine phi, and then cosine phi. The computation of t theta and t phi, they're doable. The cross product is really messy, and I think that most instructors would just be happy if you would remember that the norm of the cross product is given by a squared sine phi, where A is the radius. And in this case, it's a unit sphere, so the radius is just 1, so I just get sine phi. Hence, I have a double integral of s, and I'm integrating z squared ds. So my z value is cosine phi, so I had cosine squared phi. T theta cross TV in norm is sine phi, and then d theta d phi. And here, my theta goes from 0 to 2 pi, and my phi goes from 0 to pi. Now notice that there are no thetas in my integrand, so this integral right here can just be written as top number minus bottom number. You don't have to do any special integration for that. And then here I have another chain rule, not chain rule, a U substitution, which is a minus 1/3 cosine cube phi from 0 to pi. And when you plug that in, you'll see that you get negative, well, it's going to be 1/3 times 2. Okay, after all the negatives are accounted for, so you get 4 pi over 3. Let's do another example, maybe a cylinder. So let S be the cylinder given by y squared plus z squared equals 4, and x between 0 and 5. So this is a cylinder that's kind of on its side. The axis of symmetry is around the x-axis, right? So the cylinder kind of behaves like this, slides along the x-axis. And along the y-axis, the y and z coordinate plane, the radius is 2. So here, I'm going to take t to be, I'm going to have two parameters. One is x and one is theta, because the radius is constant. This is going to go to R3, and t of x theta, well, x will just stay x. Theta goes from 0 to 2 pi, but each one is going to be, the one coordinate is going to be 2 cosine theta, and the other coordinate is 2 sine theta. So tu is going to be equal to, there's no tu, the tx is equal to 1, 0, 0, and t theta is u minus 2 sine theta 2 cosine theta. So let's compute the cross product. Ijk 1, 0, 0, 0 minus 2 sine theta 2 cosine theta. The first term is 0. The second term is negative. There's an inherent minus sign, negative 2 cosine theta. And here I have a negative 2 sine theta. All right, so if I compute tx cross t theta in norm, I get 4 cosine square theta plus 4 sine square theta, which becomes the square root of 4, which is a 2. So let's integrate, say, x plus z, right? So find the integral over the cylinder of x plus z ds. The first part is only figuring out what the surface element is. And then here, as we remember, this guy is interpreted to be the density. So now we're going to keep the x, but we're going to move everything to theta. Z is equal to 2 sine theta. The area element, the surface area element is 2, okay, dx d theta. X goes from 0 to 5. and then theta goes from 0 to 2 pi. Now, this integrand right here has both x and theta. So for now, let's just keep both of them, although I'll show you in just a moment how you can simplify this really quickly. Let's pull the 2 outside, and let's integrate in x. So you have a 1/2 x squared plus 2x sine theta from 5 down to 0. And remember, these are x values. Okay. So my x values will give me a 25 over 2 plus 10 sine theta d theta. Okay, so now we have 2 times 25 over 2 theta plus, or minus rather, 10 cosine theta from 0 to 2 pi. Now, this gives me 0 because I have 1 minus 1 there. And then I have a 2 times 25 over 2 times 2 pi, which is 50 pi. Now, notice that this trigonometric part actually winds up disappearing. But where did it come from? It came from this piece right here. And notice that this piece right here only depends on theta, and theta is going from 0 to 2 pi. And what happens is that when you integrate sine over an entire period, there's a positive part and a negative part that cancels each other out. So if you use that idea right there, then you could have gotten rid of this in the first place. And you can appeal to symmetry to cross that out. That gives you a lot of extra time. If you're pressed on an exam, you can make your integration a lot cleaner by removing bits that you know are not going to contribute anything. Let's go on to a fourth example, and this is a paraboloid, right? So compute the double integral of s z ds of the paraboloid. Maybe I should say where s is the paraboloid given by z equals x squared plus y squared, and then z is less than or equal to 1. Here, what kind of picture do we have? We have a paraboloid like this. It is shaved off at the top by the plane z equals 1. And so we have to parametrize this carefully. Now, if I set, um, if I set, let me get these colors right. If we set 1 equals x squared plus y squared, that's essentially trying to identify this circle up here, right? It's a unit circle, and what you want to think about is you want to bring that circle down to the xy plane. Okay. And so you're going to be integrating over a disk, right? So, right, this is a circle of radius 1, okay, which is parametrized, okay, by r and theta, polar coordinates. So define the parameterization t. R is going to go from 0 to 1, and then theta will go from 0 to 2 pi. This is going to be given by, well, x is r cosine theta. So let's write this down. T of r theta is r cosine theta, r sine theta. And notice that when I plug in x and y here, I get r squared cosine squared theta plus r squared sine squared theta. That comes from this expression right here. And so I can write r cosine theta, r sine theta, and then r squared. TR is equal to cosine theta, sine theta, 2r, and t theta is equal to negative r sine theta, r cosine theta, 0. And then tr cross t theta is equal to ijk cosine theta sine theta 2r, negative r sine theta, r cosine theta 0. So let's take the cross product. I have a negative 2r squared cosine theta. And then on the other side, I have a negative 2r squared sine theta. And then here I have an r cosine square theta plus r sine square theta. And this entire thing is just equal to r. So tr cross t theta equals 4r to the fourth cosine square theta plus 4r to the fourth sine square theta plus r squared to the 1/2 power. These two terms combine just to give me 4r squared, 4r to the fourth plus r squared. The whole thing is underneath a square root. And then I could pull an r square out, which becomes under the square root, it becomes an r. And then r to the 4r to the second plus 1 is what we get. So let's compute the surface area or the surface integral z ds of this paraboloid. Z, what is z equal to? Z is equal to r squared. So z is equal to r squared. And then here I have r square root of 4r squared plus 1, dr d theta. R goes from 0 to 1, and theta goes from 0 to 2 pi. Now notice that the integrand doesn't have a theta inside of it, so I just get a 2 pi times this integral right here. Now, for reasons that we'll see later, I'm going to keep these two separated and not write it as r cubed. Okay. This problem is much more an integration problem because it requires two integration by parts. This is one of these tricky integrals that you see in Calculus 1. So what I'm going to do is I'm going to let this be du, and this is going to be v. So v is equal to r squared, dv is equal to 2r dr. Okay. Du is equal to r square root of 4r squared plus 1. And then I mean, the more that you can do this in your head, the better. This is going to be 1/2. This is going to be 3/2, 2/3. And then I have a 8r, so I have a 1/8. So right here, I have a 1/12 times 4r squared plus 1 to the 3/2. So this integral is going to be a big integration by parts. First, I have VU, which is r squared over 12, 4r squared plus 1 to the 3/2 integrated between 1 and 0, minus the integral of u dv, which will give us a 2r over 12, 4r squared plus 1 to the 3/2 dr. Let's just clean this up a little bit. If I plug in first of all, if I plug in a 0 into r, I get nothing. If I plug in a 1, I get a 1/12 times 5 to the 3/2. And let's just clean this up a tiny bit. Let's bring the 1/6 out. And then again, r, 4r plus 1 to the 3/2 dr. 2 pi times 5 to the 3/2 over 12 minus 1/6. Let's do an integration by, this is not an integration by parts, this is an integration by u substitution. So this is a little bit easier. 4r squared plus 1 to to the 5/2. And then I have a 2/5, and then I have a 1/8. This is integrated from 0 to 1. And hence I have 2 pi. I'm going to write this as 5√5 over 12 minus 1/6. This little fraction out here is 1 over 20. Oh, let's see, 1 over 20, right? And then I plug in the 1, I get a 5. I plug in the 0, I get a 1. So I get a very multi-layered expression. Let's try to clean this up a little bit. Minus 120, 1 over 120, 5 to the 5/2, plus 1 over 120. So let's factor out a 1 over 120. The effect on this piece right here is that you actually multiply it by the top by 10, so I get a 50√5 minus, and I'm going to write this as 25√5 plus 1. So I get pi over 60 times 25√5 plus 1. And that's the answer. Now, in a supplementary video, we will go over more difficult regions like triangles or segments of planes where after the parametrization, you do not have a rectangle. Those are a little bit more complicated, and we'll save those for the supplements. But let me give you an idea about how to integrate over symmetric regions. So suppose that I'm asking you to integrate x ds. Okay, integrate this object right here over the unit sphere. Now, the unit sphere is very, very symmetric in all directions. And notice what happens is that in the unit sphere, the x is positive half the time, and then it's actually negative half the time. So if you think about cutting the sphere into two pieces with a plane through the YZ coordinate plane, then half of the x is on one side and half of the x is on the other side, and they just happen to be opposite signs. So what happens is that you would expect this object to be 0. Okay, we expect by symmetry that the integral is 0. So let's just remember our parametrization. X is equal to cosine theta sine phi, and then ds is equal to sine phi d phi. And therefore, when I integrate this object right here, I get cosine theta sine phi times another sine phi, okay, d theta d phi, right? The theta gives you a 0 to 2 pi, and the phi gives you a 0 to pi. Now, I can split these two because I have an integrand that is a product of functions of theta and functions of phi. So I can write this. Now, this guy is non-zero, but who cares? Because this object right here is 0. If you integrate it, you get sine theta from 0 to 2 pi times, who cares what this is? And if you think about it, when you plug in 2 pi and 0, you just get 0 both times, so this entire thing is 0. But if you're quick, you can tell yourself, wait, look, I see that there's a symmetry at work here, and I don't really need to do all of these integrations if I'm running out of time. Let's pick another example. What if I had y z squared ds. Okay, so integrate this over the unit circle sphere. So here, y, let's just think about y, right? So I have x, y, z. This object is always going to be positive. So this object right here, this y, you think about it, so similar to the x in the previous problem, this y is going to be positive half the time and negative half the time. So this y is going to cancel out and leave 0. So let's just verify that that's the case. Sine theta, sine phi, z is equal to cosine phi, and then ds is equal to sine phi d phi. So my integral is going to be 0 to 2 pi, 0 to pi. Y is sine theta, sine phi. Okay. Z is going to be a cosine squared phi. Right? And then I have another sine phi lurking out back here. So this is my y, this is my z squared, and this is my ds. Now, I can break this up into an integral with just sine theta, and then the rest of it goes with the phi. Now, this guy is non-zero, but who cares? Because this object is 0, right? Similar to the previous problem. If I integrate over an entire cycle of sine, the positive part and the negative part cancel out. And if you trace where this actually came from, it just came from the y, which we know was positive half the time and negative half the time. So that cancels out. In fact, if you're integrating over the unit sphere, right, over, with f of xyz equal to some, positive power of x, some power of y, and some power of z, then the double integral over the sphere is going to be 0 whenever any of m, n, or p, right, is odd. If I have a single odd value in any of the exponents, integrating over the unit sphere, I will get 0. So for example, if I'm integrating x squared y to the 100 z to the 67, okay, the fact that this guy is odd immediately tells me that this is 0. Now, this doesn't, you have to be careful, this doesn't work if the cancellation is not true. So however, right, um, if all the if all of m, n, and p are even, then the integrand is always positive. So the integral is positive. And then you're just going to have to, for example, if I have x to the second, y to the fourth, z to the sixth, the s, then you would have to work really hard. Right? This requires a lot of work. Okay. And it's most likely that you're not going to have a problem like that, or you can get some kind of calculating software to figure that out for you. Another time when you have to be careful is if you have a hemisphere. If S is a hemisphere, say the unit hemisphere with Z positive, here I have just the top part, then if I have the previous example, x squared, y to the 100, z to the 67, ds, this object right here is no longer going to cancel. It's not canceling. It's always positive because of the region. And so this object here is not zero, and it would be really, really difficult to compute this particular one, but you have to be careful not to be hasty and say, oh, odd must be zero. You have to look at the region and what's odd. Okay. Now here's a nice trick. Okay. So here's a nice trick. Compute the double integral of x squared ds over, say, where S is the circle, the sphere of radius A centered at the origin. Now, one way to do it is to parametrize and all that stuff, but you actually don't really have to. If you just think about symmetry, think of symmetry, right? On a sphere, the x, y, and the z coordinates have all the same behavior. So there's every reason, right, to believe that if I just replace an x with a y, I receive the same answer. And similarly, when I replace x with z. So these three terms are actually the same, right? So we're on a sphere, and the roles of x, y, and z are pretty much identical. If I flip two of them, um, or replace one with another one, I don't really change the value. So what I'm going to do is I'm going to add these three things together. Okay. So basically, three of these is equal to x squared ds plus y squared ds plus c squared ds. And then I have x squared plus y squared plus z squared ds. Now the thing is, I'm on a sphere of radius a, so x squared plus y squared plus z squared is actually a constant a squared. Okay. And so I can bring the a squared out, and then I just have a ds right here. And the ds, right, what is this object right here? This object is just the surface area. So the surface area of a sphere of radius a is 4 pi a squared. And so the final answer, no, yes, 4 pi a squared. And so my final answer is 4 pi a to the fourth. Now, we're not quite done yet because we had three of these. Okay. And so my final answer is x squared ds is equal to 4/3 pi a to the fourth. And notice that this is a generalization of a computation we did earlier. The computation that we did was that we integrated over the sphere right here, z squared, and we got 4/3 pi. This is a sphere of radius 1, and here we have a sphere of radius a, so there's a factor of a to the fourth that pops out. So that's the conclusion of this segment. There will be supplementary videos on additional types of regions, triangular regions. We can do a helicoid region, and other ways of thinking about the surface integral. Remember that the surface integral computes the mass of a surface given when the function is interpreted as the density, but the density of the surface can, in this interpretation, be negative at some places and positive at other places. So it's really kind of a net mass in a sense. All right, so that's the end of that video. The next video will be on surface integrals of type 2. which include vector fields and flux. So we will see you then.